everyone, today we study Calculus 2, double integrals over long rectangular regions. We assert the double integral on a general set D. Firstly, let's review the geometrical meaning of double integrals. If fxy is greater than 0, the double integral of fxy on D represents the volume of curved top cylinder below the surface Z equals fxy and above the region D. If fxy is less than 0, the double integral of fxy on D represents the negative value of the volume of curved top cylinder. If fxy is both greater than 0 and less than 0 on region D, the double integral of fxy on D represents the algebraic sum of volume of the cylinder. We firstly see this kind of integral domain. X is from A to B and Y is from phi 1x to phi 2x. Phi 1x and phi 2x are continuous on the interval AB. The two pictures are this kind of integral domains. We call it X-style integral domain. A set D is X-style integral domain if it is simple in the y direction, meaning that a line in this direction intersects D in a single interval, or point or not at all. Now we give the computation method of double integral by geometrical meaning. If fxy is greater than or equal to 0, the double integral of fxy on D represents the volume of curved top cylinder under the surface Z equals fxy and above the region D. Now we calculate the volume of the curved top cylinder in a different angle. Area of parallel cutting plane is given to calculate the volume of cylinder. Any x0 belongs to AB. Compute the cutting plane area. The area of the red place AX0. We can calculate the area of the cutting plane by definite integral. X is integral variable. X is from phi 1 as 0 to phi 2 as 0. The curved function is Z equals fx0 y. So ax0 is equal to the definite integral of fxy from phi 1x 0 to phi 2 as 0 with respect to y. Replacing x0 with arbitrary x belongs to the interval AB, we obtain this formulation. According to the formulation of volume of the given area of parallel cutting plane, the volume of the cylinder is equal to the definite integral of AX on the interval AB. Replace the expression of AX into the integrand function. We get the double integral of fxy on D is equal to this formulation. Usually, it is written as this compact form. We call it an iterated integral. First, integrate on y, then on x. Notice that in the inner integration, x is fixed. Note that if fxy is greater than or equal to 0, The physical meaning of the double integral represents the quality of non-uniform thin slice with surface density fxy. Ax is equal to the definite integral of fxy from phi1x to phi2x with respect to y. This is the quality of the rod. So the double integral is equal to the quality of non-uniform thin slice. We secondly see this kind of integral domain. Y is from C to D and x is from phi1y to phi2y. Phi1y and phi2y are continuous on the interval CD. The two pictures are this kind of integral domains. We call it Y-style integral domain. A set D is Y-style integral domain if it is simple in the x direction, meaning that a line in this direction intersects D in a single interval or point or not at all. After the same derivation process, we first calculate the definite integral on x, the definite integral of fxy on the interval phi1y and phi2y, then calculate the definite integral on y. Usually, it is written as this compact form. We call it an iterated integral. First, integrate on x, then integrate on y. Notice that in the inner integration, y is fixed. The third kind of integral domain is both x-style and y-style. We can choose the suitable one according to the characteristic of integrand function. If the integral domain is neither x-style nor y-style, it can usually be considered as a union of pieces that have one or the other these properties. For example, if the domain is like the right finger, it can be divided into three x-style regions. By additive property of integral, we have the double integral on D is equal to the sum of double integral on D1, the double integral on D2, and the double integral on D3. Next, let's give some examples to grasp the above method. Example 1. Please find the double integral of the square of x over the square of y on the region D, where D is the closed domain enclosed by a straight line s equals 2 and y equals x, and hyperbolic curve xy equals 1. According to the right picture of D, D is the x-style region. X is from 1 to 2 and y is from 1 over s to x. The double integral can be converted into an iterated integral. First, perform the inner integration with respect to y from 1 over x to x. Then perform the outer integration with respect to x from 1 to 2. For the inner integration, x is fixed. The primitive function of the inner integral is negative value of the square of x over y. Then calculate the difference between the function value of the primitive function at the upper and the lower limit of the integral. We obtain negative x plus cubic x. Lastly, calculate the definite integral of negative x plus cubic x from 1 to 2 with respect to x. The result is 9/4. This problem can also be solved by regarding D as the y-scale region. But we must divide D into two y-scale regions in y equals 1. We denote them by D1 and D2. The double integral on D is equal to the sum of the double integral of D1 and the double integral on D2. As for D1, y is from 1/2 to 1, and x is from 1/y to 2. As for D2, y is from 1 to 2, and x is from y to 2. These two double integrals both can be converted into iterated integrals. First, perform the inner integration with respect to x. Then perform the outer integration with respect to y. From these two methods, we can see that the first method is more simple. So, try not to block processing if it is possible. Example 2. Evaluate the iterated integral of double y times e to the power x for y from 0 to 1 and for x from 0 to the square of y. First, perform the inner integration with respect to x on the interval 0 and the square of y. Y is fixed. The primitive function of the inner integral is double y times e to the power x. Then calculate the difference between the function value of the primitive function at the upper and the lower limit of the integral. We obtain double y times e to the power y squared minus double y. Lastly, calculate the definite integral of double y times e to the power y squared minus double y from 0 to 1 with respect to y. This definite integral can be divided into two definite integrals according to the linear properties. The final result is e minus 2. Example 3. Change the order of the integration. The integrand is f(y). Integrate from 0 to 1 for x and from 0 to 1 minus x for y. The region D is shown in the right figure. The original iterated integral regards the region D as the x-style region. Now we need to change it into y-style region. Y is from 0 to 1, x is from 0 to 1 minus y. So the result is this. Example 4. Evaluate the given iterated integral of x squared times e to the power negative y squared for y from s to 1 and for x from 0 to 1. Notice that in the inner integration, the integrand e to the power negative y squared does not have any derivative in terms of elementary functions. We can change the order of the iterated integral. The detailed process is as follows. Step 1. Use inequality to express the integral region D. X is from 0 to 1, y is from s to 1. This is considered as x-style region. Step 2. Draw the picture of D as in the right side. Step 3. Change D into y-style region. y is from 0 to 1, x is from 0 to y. The original iterated integral is equal to the double integral of x squared times e to the power y squared on region D. Regarding D as the y-scale region, we can get this iterated integral. First, fix y and integrate from 0 to y, and then integrate the result on y from 0 to 1. The inner integration is equal to 1 over 3 times the cubic of y times e to the power negative y squared. Lastly, calculate the definite integral with respect to y, and we obtain the result. It is 1 over 6 minus 1 over triple e. Notice that in computing double integral, it is important to select the proper order of the integration. The following form of integral must put in second order of integral. For example, the integral of sin x over x with respect to x, the integral of sin the square of x with respect to x, the integral of 1 over ln x with respect to x, and so on. Example 5. Calculate the double integral of the absolute of y minus x squared over d. Where d in problem 1 x from negative 1 to 1, y from 0 to 1. In problem 2, x is from negative 2 to 2, y from 0 to 1. We consider problem 1 firstly. The picture of rectangle D is in the right side. Notice that the absolute value of function of integrand has positive and negative value on D. So we need to divide D into two parts. In the red part, denoted as D1, y is larger than or equal to the square of x. In the green part, denoted as D2, y is less than the square of x. According to the adjective of double integral, the double integral on D is equal to the sum of the double integral on D1 and D2. The integrand of double integral on D1 is y minus the square of x, and the integrand of double integral on D2 is the square of x minus y. These two integrations can both be converted into iterated integrals according to the A-style regions. That is, first integrate with respect to y. As to the first integral, y is from x squared to 1, x is from negative 1 to 1. As to the second integral, y is from 0 to x squared, x is from negative 1 to 1. The final result is 11 over 15. Now we consider problem 2. The picture of rectangle D is in the right side. The same as in problem 1, we need to divide D into two parts. In the red part, denoted as D1, y is larger than or equal to the square of x. In the green part, denoted as D2, y is less than the square of x. The double integral on D is equal to the sum of the double integral on D1 and D2. Notice that the double integral of y minus x squared on D1 is the negative value of the double integral of x squared minus y on D1. So we have 2 times of the double integral of y minus x squared on d1 plus the double integral of x squared minus 1 on d. These two integrations can both be converted to iterated integrals according to the x-style regions. That is, first integrate with respect to y. As to the first integral, y is from x squared to 1. X is from -1 to 1. As to the second integral, y is from 0 to 1. X is from -2 to 2. The final result is 22/5. Now we introduce the symmetry that is important in simplifying double integral calculation. Property 1. If the domain D is symmetrical about the x-axis and fxy is even function with respect to y, that is, fx negative y is equal to fxy. The right side D is such kind of picture. Then the double integral of xy on region D is equal to 2 times of double integral of fxy on region D1. If fxy is odd function with respect to y, that is, fx negative y is equal to the negative of fxy, then the double integral of fxy on region D is equal to 0. Property 2. If the domain D is symmetrical about the y-axis and fxy is even function with respect to x, that is, f negative xy is equal to fxy. The right side is such kind of picture. Then the double integral of fxy on region D is equal to 2 times of double integral of fxy on region D1. If fxy is odd function with respect to x, that is, f negative xy is equal to the negative of fxy, then the double integral of xy on region D is equal to 0. Property 3. If the domain D is symmetrical about the origin, then divide D into two symmetrical parts, D3 and D4. If fxy is even function with respect to x and y, then the double integral of fxy on region D is equal to 2 times of double integral of fxy on region D3. If fxy is odd function with respect to xy, then the double integral of xy on region D is equal to 0. Let's see some examples. The domain D is circular domain. Let D1 is an upper semicircular domain. Then the double integral of the square of y on D is equal to 2 times of the double integral of the square of y on D1. The double integral of the cube of y on D is equal to 0. Let D2 is a right semicircular domain. Then the double integral of the square of x on D is equal to 2 times of the double integral of the square of x on D2. The double integral of the cube of x on D is equal to 0. This class, we study the double integral on general set D. The first domain D is x-del. The double integral can be converted into an iterated integral. First, integrate with respect to y, Then integrate with respect to x. The second domain D is y scale. The double integral can be converted into an iterated integral. First, integrate with respect to x, then integrate with respect to y. The third domain D is both x scale and y scale. We can choose the suitable one according to the characteristic of the integrand function. Try to understand and master the above knowledge. Thank you. See you next time.